All right, thank you everybody, and I'm William, based in the University of Southampton, and please bear with me for a period of time because I am already the last one in the morning session. Okay, so my PhD is project is about the freshwater fish and underwater acoustics, which is developing a method of measuring the resonance property of fish swim bladders. So, as we mentioned many times before in this morning, rivers, beautiful rivers, they are the veins of the Mother Earth, and sadly, a lot of them has been blocked and fragmented by all kinds of infrastructures like dams, causing a lot of problems for the loss of biodiversity, and among which also fish suffers a lot. Like 22% of fish passing through turbines will get killed, and for longer fishes like eels, which is also an endangered species, the survival rate versus turbines is less than 40%. So the research question is, can we scare fish away from resonating their swim bladders? So what is swim bladder? So we're all fish experts, and right now I have to invite an old friend of mine from our last meeting in Poland, my favorite fish. And their swim bladders is a very important gas-filled organ in their body and helps to control their buoyancy and also the swimming stability. And also it contributes to their sensory of sound. And the acoustical properties of fish swim bladders has been widely used in marine science like fish finders, echo sounders, fish resonance, all kinds of stuff. But the application of the resonance properties of swim bladders in freshwater ecosystems is very underdeveloped. And then the next question is, what is resonance? So here is a similar example of a resonating balloon. So when the balloon is resonating, the wall of it is actually vibrating to the greatest magnitude. Slow-mo is like this. But this balloon is being resonated by a mechanical inertia shaker. So it's slightly different, similar but slightly different from what it is when it's resonated by sound waves. So here I got a balloon, which is another form of swim bladder. So when I try to excite it with my voice in high pitches like this, my fingers are not feeling the vibrations very much because it's far away from the resonance frequencies of itself. But when I use a low frequency wave sound like this, my fingers can feel that it's vibrating a lot comparing to the high pitches, even if I'm using a much quieter level of my voice. So swim bladders like this balloon will resonate at the right frequency by sound, which is called resonance frequency, a very important role in today's topic. And the wall of it will vibrate to the greatest magnitude when it's resonating, and also, of course, the air cavity inside it. Normally, a bigger bubble gets a lower resonance frequency. And then, what is underwater acoustic? So normally, underwater acoustic is famous for detecting targets underwater, like this, a submarine or ship, anything. But sadly, the sound, especially low frequency sound that we're going to be using, will not travel very freely in most freshwater ecosystems like rivers because it suffers from a lot of strong reflections and complicated reverberations within the river. As you can see, the river is very shallow, so the acoustic wave will bounce a lot of times. So what can we do in such condition? So right now, can we switch this submarine with a fish? Hopefully we can. And instead of insonifying the whole ocean with sound waves, can we only take out a very small volume of water and only insonify this volume of water. So that's where we got. So the first experiment I had is with a black, a little bit ugly impedance tube, which both of the lid on both ends can be removable, and there is an inertial shaker attached to it to transmit sound waves and sound energy into the water body. And then we put balloons, dummy swim bladders, and dead fish inside the tube. So when it's without anything, like water-only tube, we calculate the frequency response of this system. And we, as we can see, we have the shaker resonance and 3 tube resonances here and here. When I introduce a balloon, something like this, into the water body, we got a very sharp peak of balloon resonance here at around 100 Hz. And but we also see the original tube modes, like the 3 peaks, has been shifted upwards due to the air-water mixture dispersion, which is also calculated by the Commander-Perspirati model. And in general, is that the presence of the bubble resonance will change the phase speed of different frequencies of the sound waves, and similar effects were also observed in other projects that with underwater acoustics and bubble acoustics. So as you can see, this is the resonance of the bladder, and it will push the original tube modes upwards and attenuate it a bit. So same as this figure here. The next step is put reasonably utilized branch out into the tube. Total number, body length are all measured, and we open their body and check their volume and calculate the equivalent spherical bubble radius. And then we got something like this in a yellow curve, which is slightly different because the bubble is smaller than the big balloons, so which result in a higher resonance frequency, and also it's more damped because it's surrounded by the fish body itself, so it's slightly more damped like this. And around here also the shift of the original modes, tank modes, are observed. Statistically, for all 18 fishes, we can see that as the body length get longer, which is they got bigger swim bladders, they got a lower resonance frequency, as expected. But I don't want to play with this heavy tube anymore, so a call for a new tank has been answered. We have a tank on the paper, a tank in the 3D modeling software, a tank on the table, and a tank filled with water. And then we got, using the same method, we got the transfer function of this, like the water-only tank. So it's slightly different than what it was because the volume, the structure, and everything has been changed, but the method stays the same. So this time, this is the shaker resonance, which is always below 50, and the first tank resonances appear at 116 Hz here, and these are maybe the second or third one. And we try my best to find the most similar fish swim bladder, similar to the real fish swim bladders, something like this, and put it into the new tank, and we get the transfer function of the dummy swim bladder inside the tank. And as you can see here, everything just is relatively similar, but damped resonance here is developed at around 178 Hz. Also, I forgot to mention that the hydrophone, the position of the hydrophone inside the tank can be changed, because I designed I designed it to be so that I can investigate the relationship of the transfer function we got versus the distance between the target and the hydrophone. So as we can see, as the hydrophone moved further away from the target, the resonance of it is the magnitude of resonance is decreasing, because the further away you got, the lower amplitude you'll be detecting. So to make a clearer view of it, I made a spectrogram of it. This is the shaker resonance at below 50 Hz, and this is the first tank resonance at around slightly above 100 Hz. And for the dummy swim bladder resonance that I showed just before, it's around here. And as you can see, when the hydrophone moves closer to it, so from a further position into the closest position, the dummy swim bladder resonance is getting stronger and stronger. So after a little processing, it becomes something like this. So, yeah, that's quite clear. For the spectrogram like this, I would expect my next experiment with live swimming fish will be that if the fish swims closer to the hydrophone, I will see a stronger resonance in the spectrogram. And when fish swims away, like into the corner or into the bottom of the tank, I would see a lower resonance. Yeah, that's the upcoming experiment. So the first thing I'm gonna investigate is the relationship between fish body length and the resonance properties of fish swim bladders. So normally, the bigger the fish is, the lower the frequency will be, but it's kind of species dependent because we got different structures and different dimensions for the swim bladder in different species. And also, I'm going to compare the difference of resonance properties between two kinds of swim bladders of different structures. For example, the figure on the left is a physiological structure of the brown trout. So as you can see, the swim bladder has only one chamber. But for carps, like crucian carps, common carps, they have much bigger and two-chambered swim bladder in their body, which might result in acoustic coupling that I'll be very anticipating to look at it. And then it's study the behavior response of fish when the fish exposed to the sound stimuli that will resonate their swim bladders. Will they have something to do with their fish hearing, or will their body sense the vibration of the swim bladder itself? That's the question we're gonna explore. And potential application, which is actually a call for collaboration in the future. The first one is to achieve, by using this technique, we're going to achieve the non-invasive diagnosis of the parasite load of the infected swim bladders of European eels. European eels are known to be a very endangered species in our area. And one reason of it to be so endangered is that they are so easily to get infected by the parasite. The parasite that will accumulate in their swim bladder. And as you can see in this figure, as the infection gets more and more serious, the volume of it will be reduced very clearly. And sometimes at the most serious part, it will almost disappear, and which acoustically means a higher resonance frequency because it's getting smaller, or no resonance at all because it has no air in it. Also, it will result in a thickening of the swim bladder wall because of the infection and the parasite living in the wall, as you can see here, which will possibly result in a higher damping factor and lower resonance peak amplitude. Another one, which is also called for calibration as well, is studying the behavior response and physiological response of the fish when they are exposed to sound stimuli that resonates with their swim bladders. For example, to monitor the startle response, swim behavior, or even the auditory evoked potentials of the fish to quantify the tolerance or the sensitiveness of the fish to the resonant tones comparing to other frequencies like 150, 300 Hertz, or broadband noise like ship noise or white noises. And also, the other one is to try to investigate the stress levels, like what Sophia did, like cortisols and other chemical indicators, heart rates when the fish are exposed to resonance stimuli, and comparing to any other acoustic stimuli. So before I end this presentation, please allow me for a moment of reminiscence. So I have this question to myself, like when and where did this idea come from? Somebody would say, like both Paul and Philip might say that it's the first year of your PhD, but actually it's from a lecture when I was attending the lecture of the ocean acoustics by Professor Paul White. He mentioned the humpback whales, how the humpback whales will try to eat or capture and eat the fish group here. So what they actually did is that they create a bubble net, and then there will be humpback whales underneath to create the bubble net and sing to it, so that the sound wave will only be traveling in the bubble wall. So the bubble wall also serves as the bubble net also serves as a sound wall, like a wall of very high intensity sound that whale scare fish away from the scare fish to be trapped them into the water body inside the net. Also, there are implications, the hypothesis that it might resonate their swim bladders as well, so that they're afraid to go through the bubbles. So when I'm where, it's actually 4 years ago in a random classroom in University of Southampton. And before I end this one, finally, I would like to thank all my supervisors and all my RIBES colleagues, Philip and James, all the other stuff. And it's really nice to meet you, and all my family's friends, and especially my wife, to support me go through the up and downs in this project. Thank you.